Hello everybody, welcome back to our graph algorithms course. Today we're going to be talking about how to represent graphs on a computer. And then after that we're going to talk a little bit about how to talk about graph runtimes and sort of how it depends on what graph you're using. So the first thing is graph representation. So from last time recall, the graph is a thing that consists of a bunch of vertices, sometimes called nodes, and also a bunch of edges that connect pairs of these vertices. And what we're going to want to do is we're going to want to do a lot of computations on graphs to determine various properties of them. But before we can get to any of that, we first need to talk about how to actually represent a graph inside a computer. And there are, in fact, several ways to do this, and exactly how we do it will affect the runtimes of some of these algorithms. So we're going to spend a little bit of time talking about that. So the first thing to do is, well, you want your vertices and you want your edges. A natural way to do this is just store a giant list of edges. Each edge is a pair of vertices, so this is sort of a big list of pairs of vertices. But now what we have is we've got these four vertices, A, B, C, and D, and then we just store a list. One is an edge between A and B, and then there's an edge between A and C, and there's an edge between A and D, and there's an edge between C and D. And this is a perfectly good way to store this graph on a computer. But there are other ways of thinking about it. One of them is the following. So at least if you have a simple graph, the only thing that really matters is which pairs of vertices have edges between them. And so if I give you a pair of vertices, sort of the only thing that you need to know is there an edge between them or is there not? So what we can do is we can just sort of build a lookup table for this. We build a matrix where you have an entry that's 1 if there is an edge between that pair of vertices and 0 if there's not. So, for example, in this graph, there is an edge between A and D, and therefore the AD entry of this matrix is 1. There isn't an edge, however, between B and C, so the BC entry is 0. And so you just fill this in and you get this nice 4x4 matrix of zeros and ones. That is another way of representing this graph. On the other hand, there's sort of a third, maybe a hybrid way of looking at things. And the idea here is that for each vertex in the graph, it's going to have a bunch of neighbors. It's going to have other vertices that have edges from the one we're considering to them. And another way of representing the graph is for each vertex, we can just keep a list of its neighbors. So vertex A in this graph is adjacent to B, C, and D. B is adjacent to A. C is adjacent to A and D. D is adjacent to A and C. So for each of these vertices, we store a list of just all of its neighbors. And that's another way to represent the graph. Now, for example, just to be sure we're on the same page, if we have the following graph, what are the neighbors of vertex C? Well, we just draw all the edges that leave C, and it connects to A and B and D, and F and H and I. And those are its neighbors. Okay, so we have these three ways of representing a graph. And it turns out that different basic operations you want to perform could be faster or slower depending on which representation you have. For example, if you want to determine if there is an edge between a specific pair of vertices, this is very fast in the adjacency matrix representation. All you have to do is check the appropriate entry of the matrix, see if it's 0 or 1, and that's your answer. Constant time. However, when you have an edge list, the only thing you can really do is scan the entire list of edges to see if that particular edge shows up. That takes time proportional to the number of edges. For the adjacency list, it's a little bit faster than that. What you do is you pick one end of this edge that you're looking for and then look for all of its neighbors. If we want to know if A is adjacent to B, you look at the list of A's neighbors and see if B is on the list. And so the time there is proportional to the degree of the vertex, the number of neighbors that this one guy has. Now, another thing you might want to do is list all of the edges in a graph. And the adjacency matrix is terrible here because the only thing you do there is you scan through every entry of the matrix and each one gives you an edge. But that takes time proportional to the number of vertices squared. However, the edge list does this very easily. It just lists all the edges in order, which is what it does. O of E time. The adjacency list is about as good, though, because you just need to, for each vertex, you find all of its neighbors. Those are a bunch of edges. And you just do this for every vertex. And this actually counts each edge twice, because if there's an edge between A and B, you count both that A is a neighbor of B and that B is a neighbor of A. But it only counts them twice, so the time is still proportional to the number of edges. Finally, if you want to list all the neighbors of a given vertex, the adjacency matrix is pretty slow here, again, because the only thing you can really do is scan through that row of the matrix and find all the ones. Now, in the edge list representation, you have to scan through all the edges in your graph to see which ones include the vertex you want. Whereas the adjacency list, you just scan through the list of neighbors of the vertex, and it's very fast. Now, it turns out that for many problems that we'll be considering this on and throughout most of the rest of this unit, what we'll really want is the adjacency list representation of our graph. Just because a lot of the operations that we need, we really want to be able to find neighbors of a given vertex. Okay, so that's how you represent graphs. Let's spend a little bit of time to talk about runtimes of graph algorithms. So when we talk about algorithm runtimes, it's generally a function of sort of the size of the input. And for most of the algorithms we've seen so far, the input sort of has one size parameter, n. And so you have runtimes like O of n squared or O of n cubed or something to that effect. However, graph algorithms, well, the graph sort of has two measures of its size, the number of vertices and the number of edges. And so the graph algorithm's runtimes depend in some way on both of these quantities. You could have runtimes like O of size of v plus size of e, which is generally considered to be linear time. But you could also have O of size of v times size of e, or size of v to the 3/2, or v log v plus e. And there are many different possibilities for types of runtimes that we have. And an interesting question, though, is, again, if you sort of only have one parameter, it's easy to compare n log n runtime versus n squared versus n cubed. But if you want to say which one's faster, say one algorithm runs in time size of v to the 3/2, and the other one runs in time size of e, it's not actually clear which one's faster. And in fact, which algorithm is faster actually depends on which graph you're using. In particular, it depends on the density, how many edges you have in terms of the number of vertices. If you have many, many, many edges, O of e is going to be worse. However, if you have few edges, it's going to be better. And in terms of density, there's sort of two extremes to consider. On the one hand, you have dense graphs. Here, the number of edges is roughly proportional to the square of the number of vertices, meaning that like almost every pair of vertices, or some large fraction of the pairs of vertices, actually have edges between them. If you're a band and you're going on tour and want to like plot a route between a bunch of cities, well, there is actually some transportation option that will get you between basically any pair of cities on the map. Now, it might be indirect or take a while, but you should still probably plot all of these out in order to plan your tour. Just what will matter is not whether or not it's possible to get between two cities, but sort of how hard it is to get between these cities. But for this time, you'll actually want sort of a dense graph that talks about sort of all pairs relations between these vertices. On the other end of the spectrum, we have sparse graphs. Here, the number of edges is small relative to the number of vertices, often as small as roughly equal to the number of vertices, or some small constant times the number of vertices. And in a sparse graph, what you have instead is that each vertex has only a few edges coming out of it. And this is actually very reasonable for a lot of models you want to think about. If you think of the internet as a graph, well, there are billions of web pages on the internet, but any given web page is only going to have links to a few dozen others. And so the degree of any given vertex, the number of neighbors that any given vertex has, is much smaller than the total number of vertices. So you end up with a very sparse graph. And a lot of things like this, like the internet, like social networks, like actual maps that you've drawn on a piece of paper, these tend to be sparse graphs. But whether or not your graph is sparse or dense will affect the runtime of your algorithms and may even help determine which algorithms you want to be run. Okay, so that's it for today. Next time, now that sort of the basics are out of the way, we're going to actually talk about some algorithms. In particular, we're going to talk about how to explore graphs and sort of figure out which vertices can be reached from which others. So come back next time and we'll talk about that.